We have combinations, 3.2. Okay, so this is different from a permutation. So permutation was all of chapter 2. Okay, permutations, where we're counting things, counting the arrangements when ordered mattered. Okay, so it mattered if we had, let's say, three things like A, B, and C. Another arrangement would be A, C, B, and then we could have A, BAC, and we could have had CAB, CBA, BCA. So these are the same three letters, but we rearranged them in so many different ways. And we said order counts. Okay, the order we put these letters count. Okay, but a combination is different. A combination is just whatever three letters that you have. Like if you have an entire alphabet, how many ways are there to choose three letters where there is no regard to order? So if I said ABC, it's going to be the same thing as saying ACB. It's the same three letters. I'm only interested in just the combination, not the actual arrangement. And I don't care where each letter is. I just only care about making that one combination. Okay. So let's look at this first example. I have here Angela, Brian, Christian, Diana, and Edward. I have 5 names, all students at this particular school named TDSS. So in question A, in how many ways could they fill the positions of president, vice president, and secretary in an election? Okay, so here we're talking about 3 specific positions. So the order is important. So we're going to use permutations for this problem. So order is important. So I'm going to use a permutation. We have 5 people to choose. So 5p3. That's my permutation. So I'm arranging 3 positions from 5 possible candidates. Okay. So that's as a factorial, it's 5 factorial over 5 minus 3 factorial, which is equal to 5 factorial over 2 factorial, and 5 factorial is 120, and 2 factorial is 2, and that's equal to 60. Okay, so we have 60 possible arrangements. Oh no, it's acting up again. I should say arrangements. I don't know why this is doing that. Arrangements to fill those positions. Okay. All right. So part B. In how many ways could these 5 people form a committee with 3 members? So now this committee of 3 members, there's no president, vice president, and secretary. Order doesn't matter. All I'm just saying, I want 3 members. So since there are no specified roles in the committee, order is not important. Okay. So I'm going to look at all the possible ways to fill the committee. Oh, why are you doing this? Committee. There you go. Okay. So possible ways to fill the committee. Well, you have, now if I use letters, let's use letters because I have these 5 people. I emphasize the letters in blue, A, B, C, D, E, just to make it easier for me to demonstrate. So if I want 3 of those 5 people, well, I could have A, B, C. Okay, but because order is not important, I'm treating A, B, C as the same thing as saying BAC, for example. It's the same 3 letters. So I'm not going to write BAC. I'm only interested in just this one possible combination ABC. I can also have ABD. And again, I'm not going to include the arrangement of DBA or BAD. It's just this is now combinations. I'm looking at just the considering this arrangement without any particular order. Okay, so ABE is another one. Okay, and then we have ACD, ACE, ADE, BCD, BDE, BCE, and CDE. So I've covered all 5 letters. Okay, so these are all kind of like unique combinations. And I don't care about the arrangements. Okay, the arrangements, the order is not important. Okay, so if I count up all these different ways, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10. So therefore I have 10. There are 10 possible ways. 5 people could be selected to form a 3-person committee. Okay, and here then again, the arrangements doesn't matter. I don't care about the order in which those people are selected. All I care about is actually forming a 3-person committee. Okay, so let's compare the 2 results from part A and from part B. So in part A, so how are the numbers in A and B related? So there were 60 possible permutations. Okay, so back in part A, if I found the arrangements of all these 5 different people and 3 ways to choose them, I had 60 possible ways to arrange them. And part B, if order did not matter, there would only be 10 possible ways that I could select this 3-person committee. So there are only 10 possible combinations. Okay, so this is not an arrangement. This is just combinations. The difference between 60 and 10, well, that's a factor of 6. So if I took 60 and I divided by 6, I would get 10. So it's a factor of 6. Or if I were to express 6 as an arrangement or as a factorial, I would say 3 factorial. Okay, because 3 factorial is 3 times 2, which is 6. So the factor is the number of possible arrangements of the 3 people in each combination, or 3 factorial. Okay, so this factor here takes care of the fact that you can take those 3 committee members and then rearrange them: A, B, C, A, C, B, etc., etc. So really, the number of combinations is going to be the number of permutations divided by the number of permutations of the selected objects or selected items. Okay. So it's a division. Number of permutations divided by number of permutations of the selected objects. So what I'm talking about here is the 60, the number of permutations, divided by the number of permutations of those three committee members, 3 factorial. 60 divided by 3 factorial. Okay. As a formula, in general terms, I'm going to express a combination using this notation: N choose R. Okay, so we're choosing from five people to elect, and we're going to make a committee of 3 people. Okay, so a combination is just a permutation of all those items divided by the permutations of those selected items. Okay, so if you expand the permutation formula, if you remember, go back in chapter 2, the permutation formula was n factorial divided by n minus r factorial. And now I'm taking that permutation formula and I'm dividing it by r factorial. R factorial being the number of ways you can arrange those 3 committee members, okay, or those items you select. And just simplifying the math here, if you're dividing by r factorial, just multiply by the reciprocal. That's what lets me keep the r factorial in the denominator. So n factorial divided by n minus r factorial times r factorial. Okay. If you're a little weak on the math, to go from this step to this step, just think n factorial, n minus r factorial multiplied by 1 over r factorial. Okay, so instead of dividing by r factorial, I'm just multiplying by the reciprocal, 1 over r factorial. And that's how I got this. Okay. So here I'm going to write on the side that the combination formula, n choose r, is equal to n factorial over n minus r factorial times r factorial. Okay. So I'm just saying that the n choose r over here is equivalent to what you have here at the end. That's just a nice packaged formula ready for you to use. So here, the notations, n choose r, c with n and r, and n choose r. This is read as n choose r in your calculator. It's the same thing as a combination. These are all equivalent. These are just 3 different notations you're going to see in different math textbooks, but they all mean the same thing. Okay, you read these as n choose r. N choose r meaning you're now looking at a combination. Okay, not an arrangement, just the combinations. So let's flip the page over. Example 2. Baskin-Robbins carries 31 flavors of ice cream. How many 3-scoop ice cream cones could you make with 3 different flavors? Okay, and each scoop is a different flavor. Now, I don't care about the arrangements in this one, so I'm going to say here order does not matter. Okay, so for example, if I chose a scoop of vanilla, a scoop of chocolate, and a scoop of mint, that's a combination. But I don't care that I put vanilla, chocolate, mint, or vanilla, mint, chocolate, or vanilla, chocolate, vanilla, mint. I don't care about the order. The arrangements don't matter. Okay, so order does not matter. All I care about is the actual combination. So if I have 31 flavors of ice cream, and I have to choose 3 of them, it's just a combination problem. Okay, so applying the formula, it's 31 factorial over 31 minus 3 factorial times 3 factorial. Okay. Now you can do the factorials on your calculator, or your calculator also has, if you look at beside the permutation function, there is a combination function, and you can use that as well. So you just do 31, choose 3 on your calculator to get the answer. I want you to try that. You should get an answer of 4,495 possible combinations. Okay. If you did 31 permutations, if you did a permutation where you selected 3 from 31, so 31p3 would equal 26,970. That number will always be bigger than the combination number. Okay, so 26,000 will always be bigger than what you get for doing the combination. The reason why is because when you're doing permutations, 31 flavors, and you're choosing 3 of them, this is now where order counts. Permutations where you have the arrangement. Okay, so I do care about whether I have vanilla as my first scoop at the bottom, chocolate in the middle, and then mint, or vanilla, then mint, and then chocolate in the top, or chocolate in the bottom, and then vanilla and mint. All those extra arrangements, that's where this number explodes. It becomes big. Okay. If all I cared about was just the actual 3 flavors, this is the number of combinations, 4,495. Okay. Example 3. Each player in a bridge game receives a hand of 13 cards. How many different bridge hands are possible? So if you don't know how to play bridge, I don't know how to play bridge, but I'm just using it as an illustration. If you have a deck of 52 cards, so I mean, again, I can bring out the playing cards, a deck of 52 cards. That's your total number of items. So 52 cards in a set. But you're dealing a hand of 13 cards. So how many different ways are there to get 13 cards? So it's a combination problem. 52 choose 13. Okay. And again, it's a combination problem, not a permutation problem. Because permutations, I would care about the order in which I'm getting the cards. Okay, I would care that the first card would be an ace or 5 or 6 or 10. But I don't. Okay, here I just care about getting the 13 cards. I don't care about the order. Order does not matter. All I'm interested in is how many combinations are there of receiving 13 cards. So it's going to be 52 factorial over 52 minus 13 factorial times 13 factorial. And that's equal to 6.3 times 10 to the power of 11 possible combinations. Right, and example number 4. So example number 4, Nathaniel runs a small landscaping business. He has 12 kinds of roses. They're like different species of roses, 16 kinds of small shrubs, 11 kinds of evergreens, and 18 kinds of lilies. These are all names of different kinds of plants and flowers. In how many ways can Nathaniel fill an order if the customer wants the following? So he wants the customer wants 15 different varieties consisting of 4 roses, 3 shrubs, 2 evergreens, and 6 lilies. So again, combinations, not permutations. I don't care about the order in which I receive the different kinds of roses. I just care about receiving 4 roses. So the number of ways of choosing roses is, if you have 12 roses to choose from, 12 choose 4. Okay? Enter that into your calculator. You get 495 possible combinations in choosing 4 roses from a set of 12. Number of ways of choosing shrubs. There are 16 shrubs, so 16 choose, and the customer wants 3, so 16 choose 3. And that's 560. Number of ways of choosing evergreens. So we have 11 different kinds of evergreens, and you want to choose 2. So 11 choose 2 is 55. The number of ways of choosing lilies. We have how many lilies here? 18 lilies. And we want to choose 6, so 18 choose 6. And that equals 18,564. Okay. Now, how many ways are there in total? Do I add them up or do I multiply? I give you a hint on the side though. Okay. And means multiply or means add. So you have to remember this comes from chapter 2, chapter 1, multiplicative counting. Okay, so if you're counting something and you're saying you want and, so if you count all the combinations of each, and you know it's and, you have to multiply all those combinations together because it's 4 roses and 3 shrubs and 2 evergreens and 6 lilies. Okay, so I'm going to be multiplying all of these together. So therefore, I have 495 times 560 times 55 times 18,564. Multiplied all together, there are 2.83 times 10 to the power of 11. So that's 283 billion. Many billions of combinations of choosing 4 roses, 3 shrubs, 2 evergreens, and 6 lilies. Okay, this is all multiplied, and I'm gonna just highlight the and, okay, and. So and right there. That's why I'm multiplying. Okay, multiply because of the multiplicative counting principle. Okay. Part B. Now, the customer wants either 4 different roses or 6 different lilies. So the wording, the language here changes the way you do the math. So the or should be emphasized. Okay. So or. So the number of ways of choosing roses. Okay. The number of ways of choosing roses. So we have how many roses again? We have 12 kinds of roses, and the customer is interested in choosing 4. Okay, how many ways are there to do that? 495. The number of ways of choosing lilies. So I have 18 lilies according to the question, and the customer wants to choose 6. So 18 choose 6. 18,564 different combinations. Okay, so how many combinations are there in total of choosing 4 different roses or 6 different lilies? So if the customer says, oh, I just want the roses, I only have 495. Or if I want the lilies, I have 18,564. In total, if I add them together, I will get 495 plus 18,564. 19,059 possible combinations. Okay, so or means add, and this is a review of the topic when we did rule of sum, when we added our different number of items and sets. Okay,